Today's lesson is going to be another one of those that sort of combines some of the skills that you've developed in the past videos. So today we're going to be working on solving trigonometric equations, and we're going to be mixing that together with some of our knowledge of identities that we now have. Before we get started, let's go ahead and take a deep breath. And let's get started. So I suppose it wasn't actually in our last lesson, but in a few lessons back, we learned that when we're dealing with really complicated trigonometric equations, our main strategy is to use algebraic methods like factoring to break a larger equation down into little pieces that are all this form. So we basically want to break things down into pieces that are sine x equals 0.3 or tangent x equals 1.2, and then solve those things using the usual methods that we developed a while ago. In this lesson, we're going to be expanding even further on that by noting that there are some expressions that can't be factored, largely because they're not all in terms of sine or they're not all in terms of cosine. When we went and did that factoring, the whole problem would be a sine problem, or the whole problem would be a cosine problem. We're now going to take our knowledge of trigonometric identities and be ready to deal with problems when we have multiple different kinds of trig functions. For this lesson, the only two identities. The only two trigonometric identities we'll focus on are going to be sine squared x plus cosine squared x equals 1, called the Pythagorean identity, and then the identity for tangent x being sine x over cosine x. We're going to learn more identities, and we'll come back and practice this method more when we learn them. So for now, it's going to be those two identities, and we're really going to use them to transform equations, kind of like what we did in the proving lesson, but not quite as strong as that. And we're going to use that to break things down, rather to rewrite things into expressions that can be factored so that we can solve them. And before we get into our handful of examples, I want to give us some guiding principles, some ideas of what we're going to be trying to do. Okay. So most of these problems revolve around one of these ideas. So the first idea is that in general, you probably want to get all of the trig functions to be of the same type. So all of them to be sines, all of them to be cosines, all of them to be tangents. Not always. There are some ways to factor, like greatest common factor factoring, where it's okay to have multiple types. But just be aware, especially if things are quadratic, you really, really, really want everything to be of the same type. The second one, it can often make sense to convert any tangent functions you have into sine and cosine, and then solve those using factoring or using other methods. So unless the problem is already all tangents, it can commonly make sense to convert tangent into sine and cosine. And then these last two things are really less about solving trig equations and more about solving equations in general. So I just want to remind you, remember that factoring and solving equations is almost always accomplished by rearranging the equation so that it's equal to 0. In fact, I'm not even sure that I want to have the word almost here. Feels to me like when you're solving equations, we get that thing equal to 0, and then we use factoring and we solve it. And then also remember that your goal is always to find a way to decompose your large equation into smaller factors that can easily be solved. So these are our guiding principles. These are the things that we're looking to try and do as we work through these complicated trig equations. So let's go ahead and take a look at our first example here. We want to solve the equation 3 sine x equals tangent x on the interval from 0 to 2 pi. One of our guiding principles was to take tangent functions and convert them into sine and cosine. I think I like that here because the other side also has a sine in it, and so it feels like we're getting some similar things together that maybe we can do some factoring with. So if I leave the 3 sine x here, and the tangent x on the other side, I make sine x over cosine x. Okay. My next thought is I really want to be factoring here. Like factoring is almost always the thing that I'm going to be used to cracking these things and solving them. So I want this to be equal to 0. I'm going to subtract this sine x, cosine x over to this side. Right? So now I'll have 3 sine x minus sine x over cosine x equals 0. Okay? Now at this point, we need to start thinking about factoring. And we've got the thing equal to 0. So if there's any way for me to factor this, that's great news. If it's not factorable, then I start looking at other ways that I can work through things. But as soon as something's factorable, we ought to look and see if we can work with it. So is this thing factorable? Is there any common factor between these two terms? And there is. You'll notice they both have a factor of sine x in them. So if I factored out that sine x, what I'm left with is 3 minus 1 over cosine x. And that has to be equal to 0. Okay? And I think the thing that I want us to take note of here is that this is really great news. Because if you look at my two factors, this one, which is just plain sine x, and this one, which only has a single trig function in it, 1 over cosine x, like, I factored this thing. Now all I have to do is use the zero product property and get, all right, so that means that sine x could be 0, or it means that 3 minus 1 over cosine x is 0. And just like that, I took a trig equation in the beginning that was fairly complicated, or I mean, at least that we couldn't solve immediately, and we broke it down into two smaller trigonometric equations. And now I just have to solve these things. So for this one, when I do the inverse sine of 0, I'm asking myself, when is sine equal to 0? Sine is equal to 0 at 0, and then at pi minus 0, which is pi. And then we can also add or subtract the period length, and the period length for sine is 2 pi, so I could add 2 pi to the 0 and get 2 pi. So great. I found 3 solutions for that one. Those are the only solutions that are going to work from the interval. Now for the other one, we've done some problems that are similar to this, and so I kind of want to ask you, pause the video for a moment, think and see if you can make sense of how you would want to solve this thing. Hopefully you recognize that what we would want to do is we'd want to move the 1 over cosine x over. And now that I have just one term equal to another term, I can use reciprocation to switch both sides around. I could make this 1/3 equals cosine x. Now this is a calculator problem. I'm going to need to do the inverse cosine of 1/3, or the arc cosine of 1/3. So for this one I got 1.23, which is on my interval, so yay. And then remember I could get another solution by doing the negative of that, negative 1.23. But negative 1.23 isn't on my interval, so I'm going to add 2 pi to find a version of that solution that is on my interval, and that gets me 5.34. So there we go. I've found 5 solutions to this equation on this interval. So now we move on to our next example. We're being asked to find all values of theta on the interval from negative 180 degrees to positive 180 degrees, which satisfy the equation 2 sine squared theta plus 3 cosine theta equals 1. Now, this equation looks a little bit like some of those quadratics that we might have solved back in an earlier lesson, like in 10b. But the issue here is that one of them is sine and the other one is cosine. And factoring is really only going to work for us if all of the variables are the same, if all of the pieces that we're working with are the same. So it's troublesome here that one of them is sine and the other one is cosine. So what we're going to do is we're going to use the Pythagorean identity. Right? We know that sine squared theta plus cosine squared theta is equal to 1. Okay? This thing will allow us to convert from sine squared to cosine squared, or from cosine squared to sine squared. Now, in theory, I could solve this thing for cosine using a square root, and I could put it in there, but I don't know that I really want to deal with this equation when it has a big old square root in it. So instead, I'm going to opt for the easier conversion. I'm going to convert the sine squared into a cosine squared. And that'll help me avoid square roots. So if I solve this for sine squared, I'll have sine squared theta is 1 minus cosine squared theta, which I could take and put in right here. Okay? So I'd like you to sort of plug that in, and so pause the video, plug that in, and get this thing to be equal to 0. If you want to work through finishing it on your own to check and make sure you can do that, that's fine. If you want to check in with me in the middle, that's fine as well. But I want you to plug this in and make sure that you can get through that step on your own. So this should be 2 minus 2 cosine squared theta plus 3 cosine theta equals 1. So all that happened there was I sort of distributed the 2 into both of these things and put them here already. Now my next thought is I know I want everything to be on the same side. I want it to be equal to 0, so I'm going to move this 1 over. So when I subtract the 1 over, this will be 1 minus 2 cosine squared theta plus 3 cosine theta equals 0. And now I'd really like Well, I'd like the squared term to be first, and I'd like it to be positive. So I'm going to do two things here. First, I'm going to multiply this entire equation by -1, right, to change the signs around. And then I'm going to reorder. I'm just going to put the 1 that's happening after the cosine. So in doing that, I'm going to wind up with +2 cosine squared theta minus 3 cosine theta minus 1 equals 0. Okay, so now I've transformed this equation that we were given. I've transformed this into a quadratic that now has only one variable expression in it. It's just cosine theta now. And so now I'm going to solve this using the same method that we did, like last week when we solved more complicated trig equations. And you may recall that in that method, what we did is we effectively did something like let m be cosine theta, so that we could rewrite this as 2m squared minus 3m minus 1 equals 0, so that we could sort of see plainly how this thing was going to factor. All right, we were able to recognize, this would be 2m, this would be m, and let's see here. Oh man, so look at that. This is not factorable, right? And because this is not factorable, I can't use factoring to solve this. So when I can't use factoring, what do I have to fall back on? We need to fall back on the quadratic formula. So since factoring isn't going to work for us here, I'm going to go ahead and use the quadratic formula. Now, some of you are fans of the quadratic formula, some of you a little bit less. Go ahead and pause the video, make sure that you can work through getting the quadratic formula answer for this. And then again, if you're feeling up to it, solve the rest of the problem. Otherwise, I'll work through it with us when you come back. So in using the quadratic formula here, we're gonna have cosine theta is -b plus or minus the square root of b squared minus 4ac all over 2a, which is going to give me 4. So cosine theta is 3 plus or minus the square root of 9 plus 8 is 17 over 4. So that means that there's two things cosine could be. Cosine theta could be 3 plus root 17 over 4, or cosine theta could be 3 minus root 17 over 4. And it's important that we sort of give thought to both of these, right? So let's look at this first one, right? 3 plus root 17 over 4. Root 17 is like 4-ish, 4.2, 4.1 or so. So when I add these together, I'm going to get 7 point something. 7 point something divided by 4, that's bigger than 1, right? Cosine can't be bigger than 1. Cosine and sine both have a range of -1 to 1, so this first one is not giving us any solutions. The other equation, on the other hand, will have solutions. On the top, we've got that 3 minus, 4-ish. That's going to be, -1-ish. -1 divided by 4, that's -1/4. That's something that we can work with. So let's go ahead now and work on solving that. Maybe the good news is this is a calculator thing, so we can get that theta is the inverse cosine of 3 minus root 17 over 4. So when we throw that into the calculator, I wound up with 106 degrees. And remember that when we're working with an inverse cosine, we're also always going to be able to find another one by taking the negative of that. The interval in this problem was -180 degrees to +180 degrees. So these are the two answers, and we're done. We've solved that equation. We now move on to our last example, when we're being asked to consider the equation 2 sine squared x minus 9 sine x cosine x equals 5 cosine squared x. This seems like a really complicated equation. It's got sine squareds, it's got cosine squareds, it's got a mixture of regular sines and regular cosines. So I'm really excited to see that the first word of part A is show. Show is so nice, right? Because it lets us know what we need to do, what we need to try and transform this thing into. So it says, show that this equation can be rewritten in the form 2 tangent squared x minus 9 tangent x minus 5. Now, I'd encourage you to pause the video for a moment and see if you can think of how you might do that. If you need a hint, think about what tangent x is. Think about what identities we have for tangent and what you might need to see in the original problem in order to get tangents to show up. Okay. If you need another hint, I would recommend that you think really hard about dividing by some amount of cosine. Okay, so now let's look at actually doing this, right? If I were to take this equation right here and divide both sides of it by cosine squared x, right? If I divided both sides by cosine squared x, I would have 2 sine squared x over cosine squared x minus 9 sine x cosine x over cosine squared x. And finally over here, I guess I'll write it out, 5 cosine squared x over cosine squared x. Okay. Now I know I recommended to you guys in the past, I've mentioned in other videos that whenever possible you really want to try and avoid dividing both sides by a variable. In this case, I don't know that we really had a choice. They wanted us to rewrite this in this form, and so we're going to do that. So I divided everything by cosine squared. On the right side, these cosine squared just drop out. Yay, great news, this is just 5. Over here, there's a cosine in the numerator, and that'll cancel with a single cosine in the denominator. So that's going to leave me with 9 sine x over cosine x. And over here, it looks like I'm just left with sine squared x over cosine squared x. But the good news, of course, is that sine x over cosine x is tangent x, and sine squared x over cosine squared x is tangent squared x. And then if I just subtract this 5 over, there we go. We finished part A. Part A of this question asked that we could asked us to show that we could transform our original equation into this one. And even before you look at part B, what is it that's nice about this last equation that we have? Well, what's nice is it's all in terms of tangent. It's a quadratic. I'm pretty sure it's even factorable, right? So now when we move on to part B and it says, hence, solve this original equation. Well, if they're asking us to solve the original equation, and we just showed that that equation is the same thing as this one, I can just solve my new, easier one, remembering to find all of the answers on the interval from 0 to 2 pi. Okay, so moving on to part B, I'm going to want to solve this thing. Okay, again, I'd recommend you guys pause the video, work through the factoring this and the solving so that you can check to make sure you understand it on your own. Many of you like to do the thing here where we let m be tangent x so that you can really see the quadratic clearly. If m were tangent x, I would have 2m squared minus 9m minus 5 equals 0. So I could factor this as 2m and m, and then a plus 1 and a minus 5. So if we double check here, that would give us a positive m and a negative 10m. Yeah, those would add. Okay, cool. So that means that my m values here would be negative 1/2 and positive 5. So now again, we think, what am I supposed to do with those things? Well, remember that m was tangent x, right? So since m is tangent x, I'm going to get that tangent x could be negative 1/2, or tangent x could be 5. And then from here, I just need to do arctangent. So the arctangent of negative 1/2 and the arctangent of 5. And these are not unit circle values, so this is the thing we need to go to the calculator for. So this first one, I got negative 0.464, which is not on our interval. We want it to be between 0 and 2 pi. So remember that I can always get solutions. I can find more solutions for tangent by adding its period length. Remember, tangent doesn't have a secondary solution, but it does have infinitely many solutions that are related to this one. So if I add pi onto this one, I wind up with 2.68. And then I could even add pi again. So give myself a little bit more space here. I could add pi again and get 2.68 plus another pi, which gave me 5.82. And then those are going to be all the solutions I can find between 0 and 2 pi. For the other one, the inverse tangent of 5, or the arctangent of 5, is 1.37, which is on my interval, yay. And I can also get another one by adding pi onto this. And when I add pi, I get 4.51. And those are all the solutions that I'm going to get to this equation. So these are the solutions to the tangent equation, but because that tangent equation is the same thing as that weird sine cosine equation, these are the solutions that we have for that original equation. So I hope that all made sense. These equations will eventually get even more complicated when we start involving secants and cosecants and cotangents, but we're going to wait a little while on that. We're going to work on some other trig skills and then sort of come back to those. So the best of luck as you're working through the assignment. As always, please let me know if you have questions.